Yeah.
We saw that in the strong coupling calculation, the effective degrees of freedom for n equals 4,
Yeah.
they were like of the same order of weak coupling.
Yes, yes, yes.
Would you expect that in other field theories that have less symmetry?
Well, so in principle, no, because the central, so this is the effective number of degrees of freedom could depend on the coupling, and as you turn the coupling large, it could decrease. Now, of course, you need to define the number of degrees of freedom in some way, and there are different ways of defining it which give different answers. So depending on how you define it, you could get agreement or disagreement. So let's consider even the case of n equal to 4 super Young mills. So you can define the number of degrees of freedom in terms of the free energy, of the thermal free energy. And then, as I mentioned in my talk, there is it goes like n squared, both for weak and strong coupling. But the numerical factor is different at weak and strong coupling, right? Now, you could define it also in other ways. You could define it by talking about the coefficient of the stress tensor correlator. So you consider the 2-point function of the stress tensor, and that's another measure of the number of degrees of freedom. So as you somehow shake the system, you excite all the degrees of freedom, and that. So if you do it that way, then you find the precise matching. And the reason, so there you need to explain why you find an exact matching, because in principle it could depend on the coupling, you would think. But in this case, it doesn't depend on the coupling because this 2-point function is also related to the 3-point function of the stress tensor through word identities. And the 3-point function is related to anomalies by supersymmetry, to anomalies in the R currents and so on. And those anomalies are exact, as all anomalies in field theories. They are the same, but they don't depend on the coupling. They are one-loop effects independent of the coupling. And so that's a way to determine this for all values of the coupling. And it explains this agreement. And in many n equal to 1 theories, you can also do this argument of computing the central charges using anomalies. It is sometimes tricky to find the correct U1R symmetry that is the partner of the stress tensor. But you can do it and you can compare it. But in general, it will be a function of the Toft coupling. So for example, Daniel Jeffreys probably will talk about an example in 3-dimensional field theories, which also has lots of supersymmetries. And there, the number of degrees of freedom changes, however you define it by some power of the coupling. Yeah?
You mentioned last time that the block symmetry at boundary due to the gauge symmetry.
Yes, yes.
What does the gauge symmetry at boundary do?
Well, there I need to refer you to Nima's lecture. Nima emphasized very much that gauge symmetries don't really exist. So you shouldn't expect them to exist in the bulk. Okay? And in fact, the boundary theory we talked about, n equal to 4 super Young, for example, n equal to 4 super Young mills has UN gauge symmetry, right? But on the boundary, you just have a gravity theory, no sign of any SUN gauge symmetry. So that emphasizes this point. And this point is very important to understand for understanding dualities and all the modern developments of field theories, that gauge symmetries are really not there, but they're redundancy of the description, and we should use them at weak coupling and so on as a way to define the theory, but we shouldn't be surprised if when we go at strong coupling we have a different gauge group, as we have in very many dualities, or we don't see it altogether. We have gravity, for example. Yeah.
You said that QCD doesn't have any parameter description.
Yes.
Could you please?
Yeah, I could expand a little more on that. So large N QCD. So QCD has three flavors and also 3 colors. Sorry, forget about the flavors. It has 3 colors. So you can consider first forget about the quarks and consider just pure Young-Mills theory with 3 colors. That has a small n. So if it is a quantum dual to quantum gravity, it will be strongly coupled with quantum gravity, because recall that the number of degrees of freedom, which in the SUN gauge theory goes like n squared or n squared minus 1, goes like 1 over the Newton constant over the size of the space, right? And to some power. And So in order to have small Newton constants, so weakly coupled gravity, you always need a large number of degrees of freedom. So that's a necessary condition. Now, if you consider pure Young mills with large n, that's expected to have a weakly coupled dual. But no one guarantees you, so in general it will be a string theory. No one guarantees you that that the size of the space in string units will be small, right? But that this size will be large. So if this size is large, then there is also a weakly coupled gravity description. So in general, large n gauge theories have a string description. It might or might not be good to approximate it by gravity description. You can only approximate it by gravity description when this also becomes large. Now, do we expect it to be large in QCD, large n QCD? So in QCD, you can find the equation for the beta function, and it turns out that sort of the, well, when you find the beta function in the planar limit, you find that the evolution equation for the 't Hooft coupling is a function of the 't Hooft coupling, okay? And so in QCD, we know that when the coupling becomes large, the theory becomes confining, and that happens at the coupling of order 1. And we expect the same to happen in large n QCD. And in fact, there are many aspects of the n equal to 3 theory that suggest that the large n is a good approximation to n equal to 3. So the fact that mesons are long-lived and so on. So if we think that the large n doesn't behave very differently from the n equal to 3, then we conclude that at the coupling of order 1, the theory will be confining. And so the radius of AdS never gets to be very large, of any dual AdS, and it's of order 1. Also, if you look at the spectrum of mesons in QCD, you find, you look at the ones that for a given spin, they have the lowest mass. This is called the leading trajectory or whatever. And you find that if you plot the spin and the mass squared, so as you increase the spin, you have this linear relationship, which can be explained as a string that rotates. The string is not breaking very quickly. That also agrees with large n. But the spacings here are all of the order of a GeV. Okay, and so there is no big split between the ones that have large spin bigger than 1, and these are open strings, so the bound is not spin 2 but spin 1, between spin bigger than 1 and less than 1. So all these should be string modes, and they have the same energies as field theory modes. So you expect the size of the spaces of the string units of the order string scale. Anyway, so these are the reasons for thinking that it will not have a controlled gravity approximation. Now, this doesn't mean you shouldn't try to use gravity and then get an idea, some toy model, and so on. But you wouldn't expect these toy models to work precisely. Yeah. Okay, so maybe I will start now. Okay, so my lecture today will be about n equal to 4 super Young mills. So n equal to 4 super Young mills is a particular supersymmetric theory. And so why should we study n equal to 4 super Young mills? Well, we know gauge theories are very important for nature. They appear all over the standard model. QCD is certainly a part of it. And we might even encounter further gauge theories in the future. So it's crucial, I think, to understand the dynamics of quantum gauge theories. And we know that the dynamics of quantum gauge theories is different than of classical or perturbative of gauge theories in the perturbative description, where the coupling is very small. And so we need to find a simple setting where we can understand the dynamics of quantum gauge theories. And n equal to 4 super Young mills is, in some way, the simplest example. Is the theory that is most symmetric. It has as many symmetries as you want. I mean, you want supersymmetry? Yeah, it has as much as you want. You want conformal symmetry? It has conformal symmetry. You want dualities? It has this duality. You want whatever you want, it has. Now, in addition, in the planar limit, it has some extra symmetry called integrability, and I'll try to explain it. Integrability is sort of the maximum symmetry you could have. It's an infinite number of symmetries. It's a super, super, super duper symmetry that allows you to do lots of calculations. As usual with symmetries, once you have more generators and it gets more complicated, it's a little more involved. I mean, anyone can do representation theory of U1 symmetries, for example. SU2 symmetries, well, it's a little harder. You supersymmetry and so on, a little harder. Now you get to integrability, well, then it's, we don't yet have a really simple description of how integrability acts and exactly how you should use it as much as, I mean, as simply as you use SU2 rules and things like that. However, I'll try to tell you what we know. Now, in some ways, okay, but of course n equal to 4 is not realized in nature, and so people sometimes say, well, I mean, it's useless to study n equal to 4 because, I mean, no, you really should be studying QCD, not n equal to 4. But sometimes it's better to study a quantum theory than just doing classical theory in QCD. So in QCD, you can do just perturbative theories. I mean, if you use PTR, for example, it only does 3-level calculations. So you would like to use some tools that allow you to do at least quantum calculations in some theory. And that might be better than just doing classical calculations. Now, it's true it's not realized in nature, so I think it's similar to saying, imagine we lived in a world where the proton had charge 2, let's say. So the simplest atom and the electron had charge 1, then the simplest atom would be the helium atom. And well, people would not be able to solve the Schrödinger equation in the helium atom, and then they might say, well, let's approximate it classically, or let's do this and that. But then someone could say, well, let's do the hydrogen atom. Let's do a hypothetical theory which has where the proton would have charge 1, and then you can solve that case. It's integrable. You can solve it completely. And then you can use that intuition to solve the other cases. And so I think n equal to 4 superior mills is similar to this hydrogen atom. It's the simplest case. And in a certain ways, it's an approximation to QCD. And this is true in some somewhat precise sense. It's the large pi expansion of QCD. So if you take calculation in QCD and you take the limit where pi is very large, it gives you the n equal to 4 superior mills answers. Now, okay, so that's motivation. Now, let's talk more about n equal to 4 superior mills. So n equal to 4 superior mills can be viewed as an n equal to 2 theory plus one adjoint hyper. And if you write this theory in n equal to 1 notation, it would have a Lagrangian, which is 1 over g squared, so trace of w squared. So these are the terms in the superpotential. Well, let me write the superpotential. This is the superpotential. This is the gauge superfield. And then you have the usual term here where you have the partner of the gauge superfield, and then you have the this adjoint hyper. So they will become a pair of chiral superfields, and here you will have a term h tilde minus phi h tilde h. Okay, this is the extra adjoint hyper. Now, can anyone tell me why I put the same coupling here and here? No, it's because, well, yes, but it's because of n equal to 2 supersymmetry. So this term in n equal to 1 notation comes from n equal to 2 supersymmetry. Now, in addition, now once you've written the theory this way, you can call each of these fields phi I, right? So phi 1 is this, phi 2 is that, and phi 3 is that one. And then this, you can see that this has an SU3 symmetry. So you can rewrite this term in the superpotential in this way. So we now have this SU3 symmetry. But this SU3 symmetry, this is an SU3 symmetry of the n equal to 1 theory. Therefore, it's an n equal SU3 symmetry of the full theory. It doesn't commute with this n equal to 2 supersymmetry. So it generates new supersymmetries. So the only way this could work is that when you act this SU3 symmetry, it generates new supersymmetries. And in this way, if you work this through, the minimal number of supersymmetries that you could have is 4. So this is a simple way to understand that the theory has 4 supersymmetries. So in other words, you do this SU3 rotation, and then you view it again as some other n equal to 2. The extra n equal to 2 supersymmetry is a different one, and so on. Okay, good. Now that's a simple argument that the theory has n equal to 4 supersymmetry. Now let me discuss the field content in bosonic in components. So we have one gauge field. We have six scalars that are all in the adjoint, and where this index goes from 1 to 6. These are the various components. So here we have 3 complex fields. Here we have 3 real fields. And then we have, for each chirality, phi alpha, we have 4 spinors. The theory has a global R symmetry, which is SO6 or SU4, which rotates the 4 supercharges. So we said that there were 4 supercharges. SU4 rotates them. And these guys are in the fundamental of SU4, and these ones are in the vector of SO6. SU4 and SO6 are the same group, different names for the same group. Now I mentioned before the SU3 symmetry, so that's if you pick a particular supercharge, that's the one you realize using superfields, then SU4 is broken to SU3, and we get that SU3 we talked about there. Good. Now, let me talk a bit about representations of the conformal group, and then we'll talk about representations of the superconformal group. So our goal here is to try to understand the spectrum of the theory, so the spectrum of states, and we'll need to understand a little bit of how to organize the spectrum and some of the properties of the representations. Okay. So now we're going to talk about simply the conformal group. Okay, so I think I missed a page here. Okay, conformal group. So has everybody seen what the conformal group is, or should I explain a little bit? I should explain? No, I shouldn't explain? No. Okay, the conformal group, we have the usual momentum generators, the dilatation and Lorentz transformations, and then the special conformal transformations, which you can view as these ones conjugated by the inversion. So the inversion is the thing that takes x to 1 over x. Now, this has dilatation eigenvalue plus 1. All these generators have dilatation eigenvalue 0. And the special conformal transformations have dilatation eigenvalue minus 1. Okay? Now, if we are interested in the spectrum of operators, so recall that operators on the plane are the same as states on the cylinder, and the energy on the cylinder is the same as the conformal dimension of the operator on the plane. Okay? And so these are states that raise the energy, and these are states that lower the energy. So if we start with some state and we start acting with these generators, we'll lower the energy, and we'd better not get any negative energy states. So at some point, this case will annihilate the operator. And so there will be so-called lowest energy or highest weight states. So lowest energy states, sometimes denoted by delta, that are annihilated by k, right? And these correspond to some special kinds of operators at the origin. These are called primary operators. And then you can generate descendants by acting with p. So you can generate this guy. And then this is just simply acting with derivatives on the operator. So the primary is essentially an operator which doesn't contain any overall derivatives. So it's very simple. Now, when you start acting with this piece, so you can get this state that has total conformal dimension delta. We can call this delta naught plus 1. Then the next one, p nu, has delta naught plus 2, etc., etc. Now, you can calculate the norms of this state. This is essentially the same as what you would do in SU2 representations. You can calculate the norms by going back here to the commutation relations. And there is a particularly useful commutation relations between P and K, which in the right-hand side contains D and M. And you can, so you can calculate the adjoint of one of these guys. When you calculate the adjoint, the P's become K's, and then commuting all the K's all the way back. So for example, let's compute the norm of that first state. So we get 0, K, P, 0, etc. Then we commute this from here. Sorry, not 0, delta 0. And then we commute this guy through here. Let's assume this, well, we can commute this to the right and then use, well, what the dimension of delta 0 will be and so on. And then, depending on, so for example, this first little thing doesn't give us anything interesting. It gives us just something proportional to the dimension, telling us the dimension is positive if we want positive norms. But well, we of course knew that the energies were positive. So something new, nothing new from here. But you sometimes get some new things from these lower ones, and you get properties that say, for example, for spin 0 states, delta 0 should be bigger or equal than 1. And if it is equal to 1, then it's a free field. Or for spin bigger than 0, you get that delta naught should minus s should be bigger or equal than 2. And if it is equal to 2, so if delta minus s is equal to 2, exactly 2, you have a conserved current. So all this you can get by simple analysis of this conformal group. And of course, for the s equal to 1 case here is familiar. That's the usual vector current. S equal to 2 is the stress tensor. Good. So probably you might have already seen this. The case with supersymmetry is very, very similar. All that you need to do is add some supercharges. Okay, we'll have some supercharges, and we have the supercharges you, of course, expect, which give the momentum. Now, how many of those are there? Guesses? 16, very good. So there are 16 of this. And, well, they have some indices, Q, alpha, I, some SU4 indices, and some these are SO4 indices. This is a spinor index. Then there is the one with alpha dot, which has the opposite SU4 index. Anyway, so there are these 16. So 4 times 2, they are complex, so that gets 16 real. Okay, but now something fun happens when you commute one of these Qs with a K. Okay? You get a new kind of supersymmetry, which is sometimes called S. So this is the analogous at the level of supercharges of the K. Okay? It has it's an extra supersymmetry you get due to conformal symmetry. And so you get 16 more, another 16 of these. You have 32 supersymmetries in total. So if we go back to that diagram over there, then the Qs have dilatation eigenvalue, which is a half, and these guys have dilatation eigenvalue, which is minus a half. So again, when we look at the representation of the conformal group, we can look for a state that is annihilated by all the S's. So all the S's are 0. And such a state is some operator, which is called the superconformal primary. This is not, well, this is basically the same as what you've been doing so far in representations of supersymmetry. It's very similar. And so in any representation of the conformal group, there will be always a state like this, as long as we consider unitary representations or representations with positive energy. Very good. And now we can generate all the other states of the representation by acting with the P's, as we discussed before, and also by acting with the Q's. So we take this delta naught, and we start acting with the Q's, and we generate a whole set of states, right? Of course, we generate an infinite number of states. Anti-commutators of Q's gives P's, and so on. We build the whole tower of states. Now, how many different operators will we get? So The S's and the Q's obey a commutation relation sort of kind of similar to conceptually to the P's and the K's. So the S's and Q's anti-commutator have a term in the right-hand side which includes the dilatation. So this whole commutator has dilatation eigenvalue 0. So here on the right-hand side we get things with dilatation eigenvalue 0. So those are the operators D. And then we have the sum-Lorentz generators. And then also we'll have the R-symmetry generators. So we get the combination of these guys. Now, if if your primary is such that delta 0 is, let's say, much bigger than their spins and their arc charges, you can somehow forget about these extra terms. And these commutators will look like creation and annihilation operators, right? So then you can do the counting for counting the number of states or number of ordinary conformal primaries you will get. Now, in other words, when you start with a superconformal primary acting with the Q's, you'll get a certain number of ordinary conformal primaries, and you'd like to know how many operators you will get. Well, how many will you get? So you'll get 2 to the number of harmonic oscillators. So here we have, let's say this is creation, this is annihilation. We had 16 of those, so we have 2 to the 16 states. So this is the dimension of the representation of the big multiplets, the multiplets when this spin is much bigger than S and J. Now, as you start making the spin small, sometimes this whole thing here in the right-hand side is a matrix. This has a bunch of indices, and you really need to analyze it carefully. But once you do that, you'll find that there will be some special cases where these matrices have 0 eigenvalues. And that means that will mean that some of these creation operators will annihilate the state, and the representation will be shorter. So again, the BPS story that you already heard about. So, okay, there are short BPS representations. Now, before I go to the short representations, I realize I forgot to say something important here, is that you have this big representation, this big massive representation, and you can ask what is the range of spins of these operators, right? And well, you have so many Q's that you can start raising the spin and by quite a while before you run out of Q's. And if you think about it carefully, maybe you can do it as an exercise, you find that the range of spins of operators goes between plus and minus 4. Okay? So, of course, it depends on the spin of the primary, but the whole range is 8, okay, in spins. That means, in particular, that you cannot have state operators with only spin, let's say, within minus 2 and 2. That would be gravity modes. Okay? So all these operators in the string theory description have to be string modes. So in the strings on AdS5 cross S5, all these guys have to be string modes. And conversely, all the gravity modes have to be in short representations. How short should they be? Well, again, the spins having half a range of that is roughly, well, you need roughly half the number of creation and annihilation operators, so there will be half BPS representations. So all the gravity modes, just by simply counting the spins, you can realize that they have to be in these half BPS representations. So examples. So what's the simplest one? So the simplest is where the superconformal primary is an operator which where we take those SO6 those scalars that have an SO6 index, and we consider the symmetric traceless contraction of the indices. So this is an operator that has some arc charge. So that matrix, that matrix there will have some 0 eigenvalues, and when you think about it, you find that it's annihilated by exactly half of the Q's. And And well, this will be the simplest BPS multiplet. I didn't consider the one that corresponds to trace of phi. I mean, I could have considered this one. This guy is especially simple because according to what we saw over there, it has dimension 1. Dimension 1 means it's a free field. And of course, this is a free multiplet. It's just simply the overall U1 of SUN. I mean, of UN. So if the gauge group was SUN, then this guy would be automatically 0. We don't have to consider it. Now, maybe another comment I should probably have made before is that n equal to 4 super Young-Mills makes sense for any gauge group. And so most of the stuff I said about representation theory also is true for any gauge group. But from now on, we are going to focus on SUN. Good. So now a special case of these states is going to be when we are going to denote the complex field C, which is, let's say, phi 5 plus I phi 6. And so we'll have something like trace C squared. This is automatically part of this multiplet. And you can check that in this case, the supercharges that annihilate these states are the supercharges that have delta minus J56 equal to 0. Okay. Very good. So I mean, roughly speaking, what is going on is, well, I mean, not roughly, exactly speaking, what goes on here is that in the right-hand side, you'll get D and then J56. And so you have that combination. What I call D there is also what I'm calling delta here. Delta is the eigenvalue of D. Okay, so this is one of them, and then there is a whole series of these guys from I1 to Ij. Okay, so these guys have this charge spin J, if you wish, under in SO6. I mean, they're in a specific representation, but just loosely speaking, let's just say they have spin J. A particular representative is trace C to the J, and so on. Okay, so we can build all these guys, and all of these are in one-to-one correspondence with supergravity modes. And indeed, they have the number of states is 2 to the 16 over 2, right? Which is 2 to the 8, and this is the same number of states we have in maximal supergravities. Now, the theory in the bulk is roughly like a maximal supergravity because it has 32 supersymmetries, so the size of the multiplet is the same as what we have in maximal supergravity. Okay, and these things with various indices, with various numbers of phi's, correspond to the various Kaluza-Klein modes of the theory in AdS5 cross S5. So all these modes correspond to supergravity modes in AdS5 cross S5. So for example, if you consider these states for very large J, they correspond to modes that move very fast on the S5. So we have the S5, there is something moving very fast on the S5. It's a particle that, from the point of view of AdS, sits at the origin of AdS and, of course, moves in the time direction. Okay, very good. Now, a consistency check of AdS CFT is the following question. Are these all the protected states? Because we already match all the protected states with supergravity modes. Now, imagine you found more protected states. So if you found more protective states, then AdS CFT would be wrong because we already cover all the light states. And well, the answer is no, there are no more protected states. So that's good. Now, are there non-protected states? Yes, there are tons of non-protected states. The simplest one is an operator of dimension 2. It's sort of the first operator you would naively write down. It's this operator. It's sometimes called the Konishi operator. That this has to do with the broken U1 symmetry. Well, let me not say why it's called Konishi. This operator has dimension 2 at weak coupling. And then as you start computing corrections, indeed will be not protected and will have corrections with some number of order chi square n. And all these corrections were computed up to the 5th order. Okay? Now, of course, this operator is not protected because it doesn't have any spin, it doesn't have any arc charges, so we have all the creation and annihilation operators that, as we discussed before.
Professor,
Now, yep. Yes?
what do you mean with protected?
By protected, I mean BPS, so that the dimension will not depend on the coupling. Yeah, maybe I should have emphasized this. The dimensions of these guys are J, and this is true for all G, all values of G square n. Yes. And the reason that the dimension cannot change is basically the same reason that people discussed before about the mass of BPS particles and so on, that they are given by the central charge. In this case, the central charge is the spin is quantized, cannot be changed, and the mass has to be linked to the central charge because it's a short representation. And we don't have another short representation we could combine into to become a long representation. Yeah.
What about 1/4 BPS or?
Yes, this is another thing I have omitted, which is that I'm discussing here single trace operators. So indeed, when you go to double trace operators, there can be 1/4 BPS and bigger things, because when you have two particles, the range of spins can be bigger than 2. So here I used the fact, I said that all single trace operators had to be 1/2 BPS states based on the range of spins. Yeah.
Can we have more than half BPS?
You mean that preserve more than half? No. Let me see.
From the computation?
Well, what will happen is that here, this is some kind of matrix, and there will be pieces where you have plus j and minus j, right? And if you cancel half of the pieces, the other half will not be canceled. But I'm sure there is a mathematical theorem that says that, but right now I don't know the quick argument. So this is not protected. Now, can anyone, well, what will be the dimension when Gn is very large? What's the guess for the dimension here of this guy? Yeah. No. But you're close, you're close. So the dimension of this guy, we said it was going to be r times the mass of the part. So first of all, we expect it to be a massive string mode, because we already covered all the supergravity modes. And the massive string modes will have a dimension, well, they have some mass, and then we multiply by the radius. And the radius goes like lambda, well, so this is r times ls, and this goes like lambda to the 1/4. So, yeah. Now then there are also some other operators which are the twist 2 operators of high spin. So again, all these guys, so here the derivatives are acting on both of these guys in such a way that we cannot pull out an overall derivative. So that's what this symbol means. This is a qualitative notation. The precise combination of derivatives is not, well, it's a little complicated, but we don't need it explicitly. So the dimension of this operator is going to be 2 plus s, so this is the ordinary dimension, plus some corrections. It's not protected again if the spin is big. And this is for Gn much less than 1. And for Gn bigger, of course, will again have some stringy mass. Now, a particular interesting case is the s going to infinity limit of these guys, which has a dimension which scales like some number, gamma cusp of lambda, times log of s. Okay? And you can understand why in the large spin limit the dimensions scale like log of s based on essentially symmetries. I mean, what goes on here is that, let's say on that cylinder, well, we said that we are computing states on the cylinder. This is the cylinder of the boundary theory. We have particles of very high spin moving on this cylinder. So when the spin is very high, these particles go very close to null lines on the cylinder. And if you have exactly null lines, then you have an extra symmetry which corresponds to essentially rescalings around this null line. The symmetry is, when the spin is finite, the symmetry of rescaling is not precise. And okay, so then in addition, you have some electric field that goes between, color electric field that goes between these two adjoint charged particles. And the energy density is proportional to this quantity. And That's why essentially you get this log of S. Well, this is probably this argument was too quick for that argument was probably too quick, but what I would like to emphasize is that there are symmetry reasons why it's log S. And then this coefficient in front is something called the Cusp anomalous dimension. And I would say this is the most important anomalous dimensions in any gauge theory. And it's very important not just because it's the only one that has been computed well, it's one that has been computed in n equal to 4, but it's because it governs many aspects of scattering amplitudes, Wilson loops, etc., etc. So in fact, it's the dominant contribution to scattering amplitudes, if you wish. It's the piece that gives you the infrared divergences of scattering amplitudes. Okay, so this was just to introduce this gamma cusp. Yes?
So when you said that these are all of the half BPS operators,
Yes.
do you just mean these are all of the local half BPS operators, or are there non-local operators, Wilson lines, and so forth?
Yes, yes. I'm only talking about local operators, operators defined at the point, which are dual to states of the field here on the cylinder. You could consider more complicated operators, and some of them can be or cannot be BPS. So there are Wilson lines that are BPS, there are domain walls that are BPS, there are all kinds of other objects that one could consider. Yeah. So now the question is whether we can calculate the anomalous dimensions for all values of the coupling. So here, for example, in this simplest case, we if we plot the dimension of the operator, so we started at 2, and then we get some correction, and then at strong coupling, so this is lambda, at strong coupling, we expect to see some fourth root of lambda, and the question is whether we can compute these corrections. Now, of course, we can try to compute them using Feynman diagrams, and that's difficult. And you can count the number of Feynman diagrams, and just counting the number of Feynman diagrams, you realize that it will be pretty difficult. But the good news is that the planar theory has some extra symmetry of integrability. Now, this extra symmetry was first seen at one loop, and then it was also seen at strong coupling. And I'm just going to give you here one simple argument. I'm going to show you how you get an extra symmetry. And this, what I'm going to show it is something that is, valid mostly from the AdS point of view. So, well, I'm going to show you an AdS argument, which then can be generalized to the full quantum theory in a way I'll just mention. So when we start with the strings in AdS 5 process 5, we have the sigma model. And the sigma model has some obvious, some SO 2,4 symmetries. So the SO 2,4 symmetries of the conformal group. Those are the obvious symmetries of the theory. We knew we had the symmetries. And my goal now is to exhibit a new symmetry. So we're going to see a new symmetry that this sigma model has. And the new symmetry can be exhibited as follows. First, we consider these directions, and in a two-dimensional field theory, we can do something called T-duality. So we can exchange the field X, so X is some field, by something which is the star in 2 dimensions of some other field dy. Okay? Let me first do this in the classical theory, and then I'll discuss the quantum theory. So in the classical theory, this is just a change of the description. And the final thing you get is that this new field y obeys the equations that would follow from a sigma model which contains these terms in the action. And now if you do a further thing, so this was the T-duality, and if you further here change C to 1 over R, here you get dy squared plus dr squared over r squared. So after this transformation, we started with AdS 5. We end up with AdS 5 again. Okay? So it looks like we didn't learn anything, but we did, because the symmetries of this AdS 5, some of the symmetries that are obvious here are actually not obvious from this point of view. In particular, the special conformal symmetries of this sigma model correspond to new symmetries. So the so the K tilde symmetries, the special conformal ones here, correspond to new non-local symmetries. Okay, so that's one argument that we have some extra symmetries, and this argument can be extended to the full AdS5 cross S5 sigma model, and even you can argue it at the level of the path integral, so you expect it to be precise to all orders in string perturbation theory, in worldsheet perturbation theory. So to all orders in 1 over square root of lambda expansion. Okay, that just tells you have the symmetry. It doesn't tell you how to apply it. I mean, once. And so the goal is of the rest of the lectures is to explain a bit how to apply this the symmetries. Turns out that once you have one extra symmetry, you have actually an infinite number of extra symmetries. I'll try to explain why that is so. And that will allow you to solve the problem. Now, integrability is a concept that you probably saw in classical mechanics. It's just saying that you have the same number of conserved charges as degrees of freedom. In quantum theories, it's just saying that you have a set of commuting operators. And in quantum field theories, which is the case we are really interested in quantum field theories, we have an infinite number of conserved charges. And the reason we typically get an infinite number is that these extra charges, well, this one here was non-local, but you can also find local conserved charges which have higher spin. And the Coleman-Mandula theorem tells you that if you have a space-time symmetry, and then the S matrix is that is beyond the usual Lorentz symmetry, the S matrix will be trivial. However, in 1 + 1 dimensions, this is not quite so. What the Coleman-Mandula theorem will tell you is that you really can have only 2-to-2 scattering. So the Coleman-Mandula theorem will still allow a kind of trivial scattering, which is 2 particles going into 2 particles again, where the momenta of the first of the 2 particles are conserved. So we have the same initial and final momenta, and this is just simply implied by momentum conservation, but we have a non-trivial scattering phase. But if we have just at least one more higher spin particle, the rest of the scattering amplitudes have to vanish, so you cannot have a scattering amplitude of the form 2 particles going to, let's say, 4 particles, okay? So, and so on. So in the end, it tells you that if you have a set of initial momenta, the set of final momenta have to be the same. And the scattering has to proceed by a scattering of 2 particles at a time. And then the extra conserved quantities are just simply sums of powers of this momenta, right? So the sum over all the particles. So this is the infinite number of conserved quantities. Very good. So here this is the situation in 1 + 1 dimensional quantum field theories with massive particles. Now, the theory we have here is, in principle, we started with a 4-dimensional field theory, but the idea is that in the planar limit, it becomes a 1 + 1 dimensional quantum field theory. So it's just the quantum field theory on the worldsheet of the string. And so the system gets this 1 + 1 dimensionality. And then we expect that, as in other 1 + 1 dimensional theories, we will be able to apply integrability, and that the way to apply it will be similar. And so that's what we'll try to do. So we'll try to apply the techniques of integrability. However, these techniques have to be modified a little bit, because the sigma model we really have is conformal, is scale invariant. It's not the same as the massive theories that have usually been considered. And even if you think in terms of Feynman diagrams, for example, when you have the various, when you're at weak coupling, you have the various particles that propagate, and the worldsheet is basically constructed out of these various gluons this really doesn't quite look like a continuous worldshed, so it's a little confusing at first sight. And so we need some tricks and some ideas for how to deal with this. And I'll try to explain some of these tricks. Oh, I ran out of time. No, what time did I start? 9:30. Okay.
15 more minutes, 12, 13 more minutes.
Okay, yeah. Okay.
Oh, you have half an hour.
Half an hour, yeah? Okay. Good.
Started at 9:30.
Yeah, sorry, I made a mistake. I thought I started at 9. Okay, so I'll just describe some ideas. So some ideas that have worked in order to produce concrete answers. They have the feel that they are not the most elegant way to do things. They're probably a simpler way to do it, but these ways I'm going to talk about are ways that do work. And probably simpler explanations will be found in the future. But I guarantee you that this way of doing things is much, 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 much simpler than doing Feynman diagrams or any other way, infinitely simpler, because you can do infinitely more than you can do with Feynman diagrams. In fact, you can get those functions we discussed there. You can get this function completely. And Pedro will discuss the final computation of that function. But okay. So before starting discussing the case of n equal to 4 super Yang-Mills, I want to do a little more review on how people solved 1 plus 1 dimensional massive integrable models. This certainly will not be a complete exposition. If you want, you can read the paper by the two Samolochikov brothers that I recommended in the recommended reading. They have a very nice description of this. And the reason I'm going to describe it is because the method that has been applied is rather similar to the method that has been applied in those integrable models. So we're going to discuss here a little bit 1 plus 1 dimensional integrable massive theories. And I'll describe some of their properties. So as I said, integrable means there are extra space-time symmetries, and Coleman-Mandel implies you have a trivial between quotes S matrix, but in 1 plus 1 is non-trivial. You have factorized scattering. So factorized scattering means that if you compute any scattering process, it can be viewed as a succession of two particle scattering processes. So here, for example, first particle 1 scatters with particle 2, and that produces a scattering phase S12. Then particle 2 scatters with particle 3, that produces a phase S23. And then here particle 1 scatters with particle 3, produces a phase S13. Okay? And so that's the final result for this 6 particle scattering amplitude. The 3 initial momenta are equal to the 3 final momenta. This won't happen in general in a non-integrable theory. But in integrable theories, the set of momenta, as I said, is conserved. And you can calculate the full scattering phase in this simple way. In particular, in integrable theories, there is no particle creation. I gave us an exercise to show that a certain quantum field theory is not integrable, and you can do it by showing there is particle creation. Now, this can be slightly more complicated when these particles have extra labels. So here I was imagining you have a single particle of mass m, so all you have in the scattering is just the phase. But sometimes these particles have internal quantum numbers, so they have an extra index A, let's say. And then this other particle has some extra index B. And then when these particles scatter, these indices A and B can be all mixed up. And what happens in that case is that the scattering phase between two particles, so we have index A, index B, C, and D, is something which has several indices. So it has A, B, and C, D. So A and B are the 2 indices of the initial particles, and C and D are the 2 indices of the final particles. I'm not saying exactly what the indices are. I mean, If you have SON symmetry, then these indices are just go from 1 to n. Let's say these particles are in the vector representation of SON. These indices go from 1 to n. If you have a supergroup symmetry or whatever, these indices will run over the set of representations of that group. Okay. But one important concept is that the whole theory, at least the theory in a non-compact space, is completely solved by saying what the two-particle S matrix is. Once you know the two-particle S matrix, you know any particle S matrix, and we know the full S matrix in the 1+1 dimensions. And that's a natural observable when we have non-compact 1+1 dimensions. Good. Now, what is the method that people have used for determining that two-particle S matrix? So solving the theory is, in this non-compact regime is equivalent to finding the two-particle S matrix. And there are two methods that have been used in the literature, at least that I know. So one is to start with a lattice model that is integrable, and then you take the continuum limit and you get the continuum field theory. And that's one way of doing it. The other way is so lattice to continuum. Is one method. The other method is called bootstrap. The name comes from, well, pulling yourself up by pulling the strings in your boots. Now, normally you would think that you shouldn't be able to do that, but the magic of integrability allows you to do some things that look exactly like doing that. So this method consists of a series of steps, which I can say, first you find the particle spectrum. So you either derive or guess. Typically, this method involves lots of guesses, or guess particle spectrum, the spectrum of massive particles of the theory. Okay, and then you write some equations for the S matrix. So there are some conditions these S matrices have to obey, like unitarity. So if you scatter 1 and 2, and then you scatter 2 and 1, so in the opposite direction, you get 1, for example, things like this. And then there is some more subtle things like crossing symmetry. And this is a rather powerful equation. Crossing symmetry tells you that if you have the amplitude for scattering particles 1 and 2 into particles 1 and 2, and now you move one of these parts, so you take the energy, the momentum and the energy of the first particle, and you reverse their signs, so you analytically continue the momentum to reverse their signs. That should give you the same as the scattering of antiparticle 1, particle 2 into antiparticle 1, particle 2. Okay? Okay, and so this together with analyticity, so we are also going to assume analyticity, some assumption about the analytic properties of the amplitude. This involves an analytic continuation, and it tells you that the analytic continued value of the S matrix is related to some other S matrix element, and that will give a non-trivial equation. And solving this non-trivial equation, you can actually find the S matrix. So I'm going to just give you a simple example of how this works. So the simple example is the Sinch-Gordon model. So it's a massive scale. It's a scalar field. It's a scalar field which has a Lagrangian 1 over g squared integral d phi squared plus mu cos phi. Okay, simple thing. So if we are at weak coupling, you expand around the minimum, you get a massive field. So what's your guess for the spectrum of this theory? What will be the spectrum of particles? How many? well, there is at least one massive particle, right? One particle of mass m. Now you can see that potentials that curve upwards are repulsive forces, and so this particle of mass m is not likely to form bound states. So we are going to guess we just have this particle of mass m. Okay. So the S matrix, as I said, is in this case is just simply a phase. So S of theta is some function, and I should explain what theta is. So we are going to represent the energy and the momentum as m cos theta, and p as m sinh theta, so that if you have energy 1 and p2, the Lorentz invariant combination depends only on theta 1, 2, which is theta 1 minus theta 2. And that's what I'm writing here, theta 1, 2. So it's a single function of a single variable. And we have some constraints on this function. So we have the combination of unitarity and something called real analyticity is that S of minus theta is equal to S of theta to the minus 1. I think I've already, this is essentially the same equation here. And then there is the crossing equation, which says that S of theta minus I pi is equal to 1. Okay. Now notice here, if we change theta to theta minus I pi, we reverse the sign of the energy and the momentum. So that's the crossing operation. Okay. Now the analyticity condition that we are going to impose is that in the theta variable, the function S will have only poles, no cuts. And the reason you can do this, well, that's why this choice of variable theta is very clever. So you, well, anyway, I won't explain the details. You can find them in the homological paper. Okay, so let's guess a solution. Okay. Well, what's the simplest guess of a function that obeys these conditions? Well, I would guess just S equal to plus or minus 1. Okay. Now, could this be equal to Sinh Gordon? S of plus or minus 1? You know another theory that has S plus or minus 1? Free theories? Or free bosons or fermions. Okay, that gives free bosons or fermions. Okay, that was too simple. So that guess was too simple. We need something a little more complicated. Okay, so we can get something more complicated by something that has some pole somewhere in theta, right? But if you have some pole somewhere, then these conditions will start producing poles at many other places. Okay, you get a bunch of poles. So once you put one, you put a bunch of other poles. And so the simplest thing is something like, the next simplest is to say something like sine, and once you sum over all those poles, you get a function roughly like this, minus I sum epsilon, sine hyperbolic of theta, plus I sum epsilon. I mean, here I could have put plus or minus I, and this epsilon could have any value, and so on. And it will still obey those two equations. So you can check that. Which one shall we check? Shall we check this one? So we change the sign of theta. We put a minus theta here. We change the sign here. Right? It will work. Now, okay, so that's an example. And then we can guess the sign by going to perturbation theory. So you can guess also that small epsilon corresponds to small coupling. And so at least when epsilon is small, so epsilon goes like g squared. And so on. And so you can check the sign by just doing the tree-level calculation there. Okay, so that's one example. I mean, and there you can then do further consistency checks that this is the right theory. You can compute, I don't know, things to two loops there and check that it matches with this and so on. Okay. Now this bootstrap technology allows you to solve the theory on an infinite line. But really, what we have in the string theory problem is not the theory on the infinite line, but we have strings on a cylinder. Because, I mean, we have a closed string. I mean, all these states we're talking about are closed string states, right? they I mean, what we're trying to do is finding the spectrum of operators is the same as finding the spectrum of closed strings inside AdS 5 crosses 5. And well, that's at least more or less similar to finding the spectrum of states in flat space, right? So you probably know how to find the spectrum of states for strings in flat space, and you always need to have a closed string. Now, finding the spectrum of an integer of the theory in a compact circle is a little more complicated. So, and I won't discuss it in detail. Pedro will discuss the technique to do this. So, recall that there is one more step to go from the infinite line to the finite circle. It's called thermodynamic Bethe ansatz. That's just the name. I won't explain it in detail. So in the rest of my lectures, what I'll try to explain is how you solve the problem on an infinite circle. So we're going to take this worldsheet, not to be a circle, but to be infinite. And so how to think about this infinite worldsheet in AdS 5 crosses 5, and how to solve it. Namely, solve it means determining the full S matrix with its dependence on the momentum, blah, 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 exactly, and dependence on lambda and everything. So that's what we will do. And this will consist of a bunch of steps. So I'll try to explain the various steps, and let me summarize the steps so that one does not get lost in the description. So the first step will be to decompactify the worldsheet. And we'll do that by taking a certain large charge limit. So a certain charge will go to infinity. So the certain SO6 charge of the states will go to infinity. And that will provide for us an infinite worldsheet. The second is to find the elementary excitations around the ground state. Now, this step is a little, I mean, really here we're doing two things. We are decompactifying the worldsheet, but also gauge fixing the worldsheet theory. So normally, when you compute the spectrum of strings, you also need to gauge fix it and so on. And here, after you do a particular gauge fixing and you take this limit, you will find that we will find that the theory is massive around this vacuum, so that we'll have well-separated excitations and so on. And then around that particular vacuum, we'll understand the elementary excitations. And then step number 3, there will be some use of the symmetries to determine the dispersion relation. This step is trivial in ordinary relativistic theories because it's fixed by relativity. But in this case, it will be fixed by the symmetries, but it will not have the ordinary relativistic form. And number 4 will be to find the two-particle S matrix. And again, we'll use these constraints of guess, analyticity, blah, 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 symmetries. And step number 5 will be to compactify on a very long circle and then understand what kind of spectrum you have on a very long circle. And step number 6 is to go to small circle. And probably these two steps I leave for Pedro, and I'll probably stop here. Maybe I'll be able to do 5, but I certainly will not do 6. Okay, so first step, decompactifying the worldsheet. So, and producing an interesting ground state. So we're going to consider the following operators in the gauge theory, with J going to infinity. So these are particular very large charge operators. It's nice to start with a BPS operator, so a state that preserves some supersymmetries, because then those supersymmetries will act on the excitations. So as I said, this operator is BPS. It takes the full supergroup of the full theory, which well has some name, PSU, well, full supergroup. It breaks it down to a particular supergroup, which is SU2/2 squared. Now, what is SU2/2? Has anyone talked in the school about supergroups? No. Well, supergroups are the same as groups, except that, and many can be represented by matrices, which have bosonic components here. So in this case, we have SU2 and SU2, and then some fermionic elements in the off-diagonal parts. Okay. So, I mean, this is just nothing else than a subgroup of the original algebra. So if you understood the description of the superconformal algebra, this is the same story. Here, when each of these factors contains a Q and an S, okay, and then the two SU2s arise in the following way. So we have SO4 in AdS and unbroken SO4 in the S5, or the internal dimensions. So this SO4 is just the SO4 rotations around the point where the operator is inserted in R4. And this one is the one that rotates the four other fields that are not involved in C. And each of these is an SU2 times SU2, each of these guys. And then, in order to build this SU2/2, you pick one of these guys with one of these guys. Okay, that will be these two parts here. And then two sets of Q's and S's that anti-commute with these guys that have the indices under, of course, the Q's. The Q's and the S's will have parts that have indices under these two or under these twos. And so, of course, the Q will have an index under the first and an SU2 index under the second group. And the same for the S's. And the final generator of such a supergroup is an element which is 1, 1, 1, 1. SU means supertrace, so supertrace of this is 0. And that generator, in terms of the original theory, we're going to call it the energy is delta minus J. So it's got the conformal dimension minus the spin. So with this definition, this has energy equal to 0. So this generator appears in the right-hand side of the supersymmetry algebra. So okay. Now, one way to understand this reduction is that we keep, so from the full supergroup, we keep all generators that have delta minus J equal to 0. Okay. So all the generators that survive are all the generators that have delta minus J equal to 0. And so recall that Q's had delta equal to a half, so there will be the J and J will be plus or minus a half, so we keep half of the Q's and half of the S's. Okay. Now the remaining generators have delta minus J equal to plus or minus a half, plus or minus 1, sorry. It's clear that this is the full range because this delta was either plus or minus 1 and J was plus or minus 1. So that's the full range of delta minus J's. The preserved ones are this. The broken ones are this. Now, why are broken generators useful? Well, Goldstone bosons, right? So if you act with the broken generators on these guys, you generate Goldstone particles. Okay. Now you generate particles. I call them Goldstone. What you do is you generate the following. So let me give examples. So if you take a trace of C to the J, and you act with, let's say, a current of the form, let's say, 5I. So some current which rotates the 5 and 6 directions, which were the two directions. So I recall that C was equal to. So if we do a rotation in direction 5I, where I goes from 1 to 4, we'll insert, let me call it both 1 plus I2. So if we act with an appropriate generator, we'll put in here we'll turn one of the C's into a W, some other complex field. And if we act again, we will generate two W's, so C J to the minus 2, and then two W's. But this W, this second W is really uniformly distributed, so the proper way to write this is really sum over J trace W c to the j w c to the j minus 2 minus j. Okay. Okay, so these are all the generators you can make, and these have delta minus j equal to 1. This has delta minus j equal to 2, and so on. So these values are determined by sort of the Goldstone properties. The reason that they are not 0, so ordinarily you are used to Goldstone bosons having 0 energy. Here they are not 0 because these generators do not commute with the energy. For usual symmetries, the symmetry generators commute with the energy, and that's why you have 0 energy. Okay. Now these are simple states. All of these are BPS states. But we can also make other interesting states by considering a state, let's say, similar to that one, but where we insert, well, let me just write it here. We insert here a phase e to the I PL. Okay? Now we should think of this as having this as a chain of Cs, and with some impurities W, which are going to propagate along this chain with some momentum. And it turns out that this particular sort of plane wave basis of momenta will diagonalize the energy operator. Now notice that the trace has a cyclic property, so if we sort of shift all the fields around in the trace, we'll get the same state. And that implies that all states should have 0 momentum. That's why to build a state with non-zero momentum, we needed 2 impurities at least. We cannot build a state with non-zero momentum with a single impurity. I mean, if we would try the same trick here, C to the L, E to the IPL, and summed over L, the cyclicity property of the trace will imply here that that momentum P has to be a multiple of 2 pi. Okay? Now this momentum defined as this is periodic with period 2 pi. Okay, but if we are really in the infinite J limit, we can forget for a second that the trace is there, pretend there is no trace, and consider an infinite chain of Cs. So we have an infinite chain of Cs, and we have this impurity W, right? I mean, we have in mind that there is here some other W, let's say, that provides an origin, or we are going to define the origin in some way. But we have this infinite chain of Cs, and now we consider such states, so where we sum over L. So this W will move along the chain. Now, how will it move along the chain? Well, before discussing the motion along the chain, so the motion will come from interactions. So a C, let's say, one of the C's can interact with one of the W's, and they can exchange positions through some of the vertices of the Yang-Mills theory. And so in this way, we'll have the C moving along the chain. I'll discuss it in more detail later. Okay. Now, let me. So right now we did this step of decompactifying the worldsheet. We are going to start discussing a bit the elementary excitations around the ground state. Yes.
Maybe it's a good time to break.
Okay. Yes. Let's stop here. So next time we'll start discussing the excitations around the ground state and discuss points 2, 3, and 4.